Good morning, class. The session is being recorded, and as always, if there's a privacy issue, make sure you always mute your audio video. Don't put anything in the chat. If you have a question, you can ask me at the end. If I ask you to participate, it's your choice. Make sure that you realize it's being recorded, of course, and will be posted for everyone. So we are looking at section 3.5. We've already looked at the derivatives and rates of change, derivatives as a function, basic differentiation formulas, the product and quotient rules, and now we are looking at the chain rule. So what we are looking at here is the addition of the chain rule. So we have looked at the good old slope, and then that's a slope given 2 points, the slope of a secant line, the slope of a tangent line, definition of a differentiation, and some differentiation formulas, including the product rule and the quotient rule. And now we are adding the chain rule, okay? So if you happen to have f of g of x and you want to differentiate, you need to use a chain rule. F is the shell function, you differentiate it, you get f prime, and then g is the inner function. By the chain rule, you multiply by g prime. So we looked at the composite function of f of x and g of x. To remind everybody the meaning of composite function, f of g by definition is f of g of x. We went through this, and then we looked at g of f by definition is g of f of x. And as you can see, we come up with the answer where the two are not the same. We also mentioned two functions. They have composite functions that are identical under the following condition. Anybody remembers the condition? When would be the case that they have the same two functions? Their composite functions are the same in any order if they are inverse of each other. So f of f inverse equals f inverse of, and in both cases, in any order, we end up with x. Other than that, that's not the case. Then we looked at the concept as to why we need the chain rule for cases such as square root of 10x plus 5 or 10x squared minus 1 to the power of 50. And there are two ways to write that. If we have f of g of x, we differentiate the outer piece, f prime of g of x, by the chain rule. We multiply by g prime. In Leibniz notation, dy dx is dy du dx. And I repeated that, and over here, one of the common ones is the power rule, and then the extended power rule. So the derivative of x to the power of n sits in front. X to the power of n minus 1, we subtract 1 from the exponent. And then we don't write anything because the derivative of x is 1. If we were to write it, we really have to write the derivative of x times 1. And the reason we don't, because it has no bearing, it makes no difference. However, if you look at the extended power rule, so we follow the same format. Instead of x, we have g of x. So n sits in front. So g of x to the power of n minus 1, so far the same. And then the derivative of g of x is not like x that it was 1, but rather something else, g prime of x. And we need to write this because the derivative of g of x is g prime of x. And that's it, okay? Then I went over these examples. If you get these examples, you really are in good shape, okay? Remember, the function is really sine, never mind the rest. Sine gives you cosine, so cosine of 2x. And then 2x is the inner function that gives you 2, so that's the answer. Again, sine gives you cosine, cosine of x squared, and then x squared gives you 2x. Now this one is sine x to the power of 2. So if you rewrite it in this fashion, it makes it easier. So look at this. N sits in front, 2. sine x to the power of 2 minus 1 or 1. And then g prime would be the derivative of the inside, the derivative of sine, which is cosine. And if we understood this, we should be in good shape. Then I looked at a simple example that can be done both ways, but not every function is easy to do in the same manner. So for example, here, y is given as u to the power of 5, and u is given as 10x cubed plus 2. If we want to go with the Leibniz notation, it's extremely simple. When we say dy du, that means differentiate this with respect to u, which is 5u to the power of 4. When we say du dx, that means differentiate this with respect to x, which is 30x squared. And basically, you're done. All you have to do, replace the u with 10x cubed plus 2 and simplify. So Leibniz notation was used, extremely simple. If we want to go with the composite function, first we have to find the composite function, which means you're going to replace. So this is f of u. So if you want f of g of x, then you're going to replace the u with g of x, which is 10x cubed plus 2. So if you are looking at f of 10x cubed plus 2, this becomes 10x cubed plus 2 to the power of 5. And now you use this extended power rule. You put the 5 in front. You write the same thing to the power of 4, and you differentiate the inside. The g prime of x gives you 30x squared. So again, this is n. G of x to the power of n minus 1, g prime of x. Okay, everybody? Now rewrite it, and it's the same answer. The point being, you can do them both ways, but remember, it's good to know both, formulas, because sometimes one is easier than the other. Now, basically, we are going to practice, practice, practice. That's all we are going to do. Okay, class? We are going to practice. So there's a lot of practice here that is needed, and you got to get comfortable with that. So let's see if we can do some work here, starting with y equals 10x squared minus 1 to the power of 50. And I do have the formula for you, the extended power rule. Some function is being raised to the power of 50. So we want to mimic this, okay, class? We want to mimic this and come up with the answer. So let me do this here for you step by step. N is 50, everybody. Okay. So we got the n. Then g of x to the power of n minus 1. 10 x squared. This is your g of x, okay, class? 10x squared minus 1 to the power of 50 minus 1, or simply 49, times
20x.
Very good. Excellent. G prime. And you're done with calculus. You just rewrite this, everybody, okay? And how do we rewrite that? We put the 20 in front, and 20x times 50 is 1000x. Let me actually erase this so you can see this clearly. Okay, everyone? So I hope it's crystal clear as to what's going on. Again, let me know if, I turned off the video just to make sure your screen doesn't get blurry. If it does, let me know, please, okay? So a little bit of a practice makes this really easy, class, okay? And I hope you are okay with that. A little bit of a practice. Let's go with the next one. We want to differentiate this. So first, we need to do something. And that means we are going to rewrite this such that we can use the power rule, everybody.
So it'd be 10x plus 5 to the power of 1/2.
Beautiful. That's the first step we need to do. Now again, let's look at the formula. And let's give everybody a chance to mimic this, okay? See if you can quickly come up with the first step, where n is 1/2, and the g function, g of x, is 10x plus 5. So we want to mimic this, everybody, okay? We want to mimic that. Let's see what you end up with. One half sits in front. Ten x plus 5 g of x to the power of n minus 1. 1/2 minus 1, which is negative 1/2. And then we need g prime of x, the derivative of the parentheses, which is simply 10. Does that make sense, everybody? So we're done with calculus. We are going to use the algebraic technique to finish the job. I hope you realize 10 and 1/2, the product is 5. This remains intact. Because this is a negative exponent, it goes down, becomes positive 1/2. Positive 1/2 means a square root. Okay, so if you want, you can write this as 5 over 10x plus 5 to the power of 1/2, and then this one. It's up to you. All right. Here's the next question. We want to find the derivative for y equals 5 times 3x minus 2 to the power of 4. It's important to know 5 is just a multiplier. It just remains as a multiplier. It doesn't do anything else. Okay, so 5 times. So you have to really differentiate this part. Okay, where this is your g function. Okay, class, that's the idea. Okay, so what do? Y prime equals, we write the 5, it's a multiplier. Now we're going to differentiate this expression using the extended power rule. 4 sits in front, so 5 times 4. We write the same thing, but we change the exponent to 4 minus 1. So it goes down to number 3. And then the derivative of it inside, the derivative of the g, 3x minus 2, the derivative is simply 3. Does that make sense? And all you have to do, multiply 5 and 4 and 3. And put it in front, number 60, and you're done. Okay. So we are looking at the chain rule, the extended power rule, and it's pretty straightforward. All right, to do this, let's remind everybody about exponential functions. The derivative for any exponential function is itself. If the exponent is x or t, you're done. But if it's not, in this case it's kx, What is the derivative of kx? K times k by the chain rule. In this case, it's not x, it's g of x. What is the derivative of g of x? G prime of x by the chain rule. So if I want to differentiate this one, I'm going to write itself. So I'm going to just repeat the same thing. Just write the same thing. Times what? Look at the exponent. It's 10x. What is the derivative of 10x? 10. So times 10 and just put it in front. Okay, everyone? I want to differentiate this. Quickly, I'm going to write the same thing, everybody. Just write the same thing. Why? Because it's an exponential function. Times what? Look at the exponent. The exponent is 2 squared. Its derivative is 2t. I'm going to put it in front. Okay. For the next one, I'm going to rewrite it first. I'm going to rewrite it as e to the power of 2t. It makes it easier. So the answer is itself, e to the power of 2t times what number, everybody? 2. Because the derivative of 2t is 2 and we put it in front. So I hope you see it's really straightforward. It's very simple, everybody. Okay. Using the chain rule or the extended power rule, if you will, very straightforward, very simple. There is really not much to it. Okay. We're going to move on. What I want you to notice in this example, we are multiplying 5x by 3x minus 2 to the power of 4. So the first thing I want to explain is about number 5. If this number is involved, meaning it's a very large number or it's a very small number, it's like, say, 5,000 or it's 1/5 or 0.218, you want to probably keep it as such in brackets, and it's a multiplier, and just keep it as a multiplier. Okay, class? The reason why, because if it's an involved number and you keep on carrying it, it becomes really crazy. But it's only 5, so you can say it's part of x, so it's 5x okay, which is the f function, times 3x minus 2 to the power of 4, which is the g function. And now I need to use the product rule in conjunction with the chain rule. And we remember the derivative is f prime g plus g prime f. So I'm going to write that in that fashion, okay, class? And then I'm going to erase. So let me write this here, and then I'm going to erase it because of f prime g plus g prime f. So what is f prime? Clearly it's 5. Yes, everybody? What is g? Just write it. you want, I can do this. Okay. Plus G prime 4 times 3x minus 2 cubed times 3 by the chain rule times 5x by the product. I hope you see how we are combining this stuff together, okay? So here's a neat writing. So let me write underneath this. This is the f function. I mean f prime, my apologies. This is the g function. This is g prime. And this is the f function. Okay, class? And you're done with calculus. Now, of course, it takes some time to finish it, and that's why your algebraic technique becomes extremely important. But look at the first step. Now, just the way it is, you can factor it, or you can see that 4 times 3 times 5, it's 60, so 60x sits in front. And now you are going to factor the 2. Okay? So everybody knows how to factor this, I hope. So let's look at what's in common. When you look at this expression, so let's actually clean it up. Let's clean it up, everybody. So we don't need this. Okay, I want to make sure that we can see what's going on. So let's see what's in common. When you look at number 5 and number 65 is in common. When you look at the expression 3x minus 2, that is in common. When you look at the exponent 4 versus exponent 3, you use exponent 3. So what do you take as a common factor? 5. Let's see if I can even write it further down. Three x minus 2 cubed. And you need to finish that. So let's see how we finish that. When you compare this one to this one, everything is there. This has exponent 4, this has exponent 3, so you'll get one of those. So you get 3x minus 2 to the power of 1, or simply 3x minus 2. When you compare this one or that one, it doesn't matter. 60x divided by 5 is 12x. Or if you compare this one, you get 4 times 3x. So take a look at the inside. Take a look at the inside. So this will give you this one to the power of 1, and this one or this one remains with 12x. 12 and 3, 15x. And that is your final answer, everybody. That is your final answer. Okay. All right. Here comes the next question. Anytime you have a fractional expression where the numerator is a number and nothing else, you don't have to use the quotient rule. You can rewrite it with your algebraic techniques as such and use the extended power rule on that. Okay. So we want to differentiate this, everybody. Using this. -4 sits in front. This is the g function to the power of -4 minus 1, which makes it -5. G prime, this is the g function. The derivative of this piece is 14x minus 1. So we have -4. We write the same function to the power of -5. So n g of x to the power of n minus 1. And g prime is the derivative of the parentheses, and we are done. I hope you realize this is in the numerator. This is in the numerator. This -5 takes it down and makes it +5 in the denominator. Okay. And so that's that. Now, here's the next one. This is a combination of chain rule and a quotient rule where the numerator is x and the denominator is 2x minus 1 to the power of 4. So you can think of this as f over g, and we are going to use f prime g. So I'm going to do it step by step. F prime 1 times g 2x minus 1 to the power of 4 minus g prime. We've done this many times before now. 4 times 2x minus 1 cubed times 2 g prime times f times the numerator f divided by g squared divided by g squared. Now the exponent is 4, we square it and we get 8. Okay, everybody? We square it and we get 8. I hope it makes sense to everybody. And believe it or not, you're done with calculus. All you have to do, simplify the numerator. And to simplify the numerator, you have to factor. So what do you factor? Let's see what we need to factor. What's in common? 2x minus 1. What exponent do you use? 4 or 3? Use the smaller of the two. So we get 2x minus 1 cubed out. When you factor, this results in 2x minus 1 to the power of 1, or just 2x minus 1. This one goes away. So you get minus 4, 2, and x. Their product is minus 8x. So take a look. You are factoring. This is algebra class. You're factoring what? 2x minus 1 quantity cubed. The first one gives you 2x minus 1, and the last one gives you minus 8x. Now, first of all, this has exponent 3. This has exponent 8. This goes away, and the exponent 8 changes to 5. That's the first thing. Now you're left with the brackets 2x with negative 8x. They add up to negative 6x. And you're done. Okay, class? It's fairly simple. Okay. Again, we really have to practice with this stuff to get comfortable, class. Chain rule combines everything for us, and it gives us a chance to practice with everything. All right. Again, we are looking at a fractional expression. We don't have to use the quotient rule. We just bring this up. And it, first of all, it's x squared plus 3 to the power of a positive 1/2 comes up, becomes negative 1/2. And now we just used it. Okay, class? So let's do that. 4, okay, it's not going to go away. 4 will be there. Times n, negative 1/2. Then g of x, just write the parentheses, x squared plus 3 to the power of n minus 1. Minus 1 gives you minus 3/2. And then g prime, the derivative of x squared plus 3 is 2x. And you are done with calculus again. Because I wanted you to see what happens, I've done this in 2 steps. 4 and negative 1/2, the product is negative 2, and 2x, the product is negative 4x. So this remains in the numerator, this goes down. Positive 3/2, and you write it in this fashion. Now, some of you may remember, and this is done. As far as I'm concerned, this is done, class. Some of you may remember this also can be written as such, but you don't have to. I'm just refreshing your memory. You don't have to write it like that, but I'm just going over another algebraic step in case. This is good enough, everybody. Okay. Let's look at the next example. Now think of it as g of x to the power of n, where g of x is 2x plus 3 over x minus 8. So let's do this step by step again. Okay, so g of x is this. So n, that means 5 sits in front. G of x, that means this piece, to the power of n minus 1. So 5 sits in front, this one to the power of now 4. We need g prime of x times the last piece is g prime of x. So g is g of x. What is g prime of x? You need to use a quotient rule on that. So let's do that. So let's recap and then the quotient rule. So 5 sits in front. You write whatever you have here to the power of 4. Now let's differentiate this using the quotient rule. F prime g minus g prime f over g squared. So the top gives you 2 times the bottom, minus the bottom gives you 1 times the top over the bottom squared. So let's see what happened step by step, class. This is n. This is g of x to the power of n minus 1. Okay, let's actually do this. I want to make sure that we understand. So this is n. This is g of x to the power of n minus 1. And this is it. Okay. This whole thing is g prime. Using the quotient rule, everybody. Using the quotient rule. Now, I hope you see that it simplifies to 2x minus 16 minus 2x minus 3, 2x and minus 2x cancel each other. We replace the numerator with negative 19. Let's rewrite the whole thing. The only change I'm making, and there's a reason for that, the only change I'm making For this one, I'm going to write it the top to the power of 4 and the bottom to the power of 4. I'm going to tell you why I do that in case you can't go from here to the last step in one shot. Okay. Now the numerator has the following 5, 2x plus 3 to the power of 4 and negative 19. So you're going to multiply 5 by negative 19, giving you negative 95. You put it at top with 2x plus 3 to the power of 4. The bottom, if you don't see from here, x minus 8 has exponent 4 here and an exponent 2, and they add up to 6. Over here, clearly, you have to add these two exponents, and you can see what happens. So again, 5 and negative 19, their product is negative 95. This remains in the numerator. These two, they just add up their exponents to give you a new exponent, and you're done. I hope everybody's okay with that. I want to look at this last question. Again, you need to practice with this. I think I mentioned that when I went over the few examples I put up for you in the beginning. So I'm going to repeat that. Okay. So I think we are okay with the video now. Let me just remind you of what I did and what I said. When you do this, I want you to read this as cosine. In fact, let me just do this. The way you read it, it makes a huge difference. For now, ignore that. Just read cosine and pause. Cosine and pause. That's it. Cosine. What is the derivative of cosine? Negative sign. Let's do that at the top. So I'm going to write y prime. Because I'm dealing with cosine, the answer is negative sign. But remember, anytime you have any trigonometric function, you have to write their argument. The argument is 3t to the power of 4. Okay, so cosine, the derivative is negative sign. Now, if this piece, everybody, was a t or theta or x, we would multiply it by 1 and we wouldn't even have to write that. But it's not, so we have to multiply by its derivative by the chain rule. And that becomes 12 t cubed, 3 times 4t cubed, or 12t cubed. Okay? And now, of course, we put that in front, and here's the final answer. So the final answer is negative 12t cubed sine of 3t to the power of 4.